We literally surround ourselves with it every single day. Yep, we rarely give it a second thought, at least not until something goes terribly wrong. I'm talking about concrete. More specifically, I'm talking about the obsessive, almost scientific precision required to test it. You see, the safety of our entire built environment, from the bridges we drive over to the high-rises we live in, relies heavily on a seemingly dry Canadian standards document known as A23.2-3C. In this explainer, we're going to unpack exactly how the standard dictates the very survival of our infrastructure.
Because, honestly, ever look up at a massive new skyscraper and wonder, how do we actually know that thing isn't just going to come crashing down under its own weight? It's kind of terrifying if you really stop to think about it. Well, engineers don't just cross their fingers and hope for the best. The real answer lies in tiny, unassuming samples of concrete, these small cylinders and beams that are tested under impossibly strict, highly regulated conditions long before the actual building is ever put to the test.
These tiny unsung heroes are formally known as compressive and flexural strength test specimens. Essentially, they're just small batches of wet plastic concrete pulled directly from the active construction site. And the standard we're exploring today? It basically acts as the strict biography, the mandated life cycle that these concrete protagonists absolutely have to follow. Because if they don't follow the exact script for how they're made, protected, and cured, well, the test results are scientifically useless, and the safety of the structure remains a total mystery.
Okay, let's dive into this. We're going to follow the life cycle of our concrete sample right from the muddy, chaotic construction site to the sterile testing lab. We'll track its birth, its perilous infancy, its maturation, a few alternate destinies it might face, and wrap up with the paper trail that proves its worth. Starting right off with Phase 1, the birth, molding the perfect specimen. This is where we extract a sample of wet concrete from the absolute chaos of a busy job site and attempt to mold it flawlessly. Now, you might think it's as simple as just scooping wet concrete into a plastic tube, right? No way. The second that concrete is sampled from the mixer, a literal stopwatch starts. According to the standard, the entire process of molding the strength test specimen must be completely finished within exactly 20 minutes. That includes lugging it across the site, remixing it, and perfectly packing it into its mold. If you take, say, 25 minutes, the chemical reactions of the cement have already progressed way too far, and your sample is totally compromised. And what's really fascinating here is how the physical state of the wet concrete dictates exactly what the technician has to do. Concrete has this property called slump, which is basically just a measure of how wet and workable it is. If the slump is greater than 40 millimeters, meaning it's relatively flowable, the technician has to pack or consolidate it by manually rotting it. But if the slump is equal to or less than 40 millimeters, meaning it's super stiff, they have to use a mechanical vibrator. You can't just guess or use whatever is handy. The standard demands the exact right tool for the exact right texture. Let's look a bit closer at that rotting process for a standard cylinder, because it is wild. You don't just dump the concrete in. You have to place it in 3 approximately equal layers. Then you take a steel tamping rod with a rounded tip and plunge it evenly all over the cross-section. Here's the kicker. When you rod the upper layers, you have to penetrate about 25 millimeters into the layer below, but you absolutely cannot forcibly strike the bottom of the mold. After all that, you tap the outer sides 10 or more times with a 0.6 kilogram rubber mallet. Why go through all this? Because these repetitive, super-specific actions force out trapped air bubbles that would otherwise become structural weaknesses. It guarantees a perfect, solid specimen.
Once that specimen is perfectly molded, it enters Phase 2, perilous infancy, surviving the construction site. For the first 28 hours of its life, this highly sensitive little cylinder has to survive right there on the active site before it's allowed to be moved.
And this perfectly captures the central conflict of concrete testing. Think about the reality of a construction site for a second. You've got heavy machinery causing ground vibrations, you've got freezing winds, scorching sun, and wildly unpredictable humidity. But what the standard actually demands during this initial curing phase is a complete oasis. The specimen has to sit on a rigid, level surface completely free of vibration. It has to be covered with a non-reactive plastic sheet so not a single drop of moisture evaporates, and the temperature right around it maintained in a perfect little bubble between 15 and 25 degrees Celsius. Creating that kind of calm in the middle of a literal construction zone takes serious effort, and specially controlled curing boxes. All right, Phase 3. Maturation, the laboratory environment. After a minimum of 20 hours in that carefully guarded site box, the sample is finally transported to the pristine lab. And even the drive over is regulated. It has to be protected from any bumps or shocks on the road. Once it finally reaches the lab, it's carefully demolded and put into a water storage tank or a moist room. And here, the temperature control goes from strictly regulated to obsessively precise. We're talking exactly 23 degrees Celsius, plus or minus only 2 degrees. The lab is required to use automated temperature recorders that take continuous readings, and those sensors have to be regularly calibrated with high-end reference thermometers just to prove they aren't drifted. And if the sample is stored in a moist room instead of underwater, the humidity rules are just as intense. The relative humidity cannot drop below 95%. The standard explicitly states that the conditions have to ensure all specimens in storage both appear moist and feel moist at all times. They usually achieve this using these crazy arrays of fog sprays or actual curtains of water cascading down the walls. But here is a detail that absolutely blew my mind. If the labs use water storage tanks, they can't just fill them up with clean tap water or purified water. The standard actually dictates the water must be saturated with high-calcium hydrated lime, specifically 3 grams per liter. Why? Because chemically speaking, pure water is hungry. If you drop a concrete cylinder into fresh water, the water will literally leach the calcium ions right out of the concrete, weakening the sample and completely ruining the test results. So, you have to saturate the water with lime first so it leaves the concrete alone. It's brilliant.
Now, not all specimens are bound for the luxury of a 23-degree lime water bath. That brings us to Phase 4, alternate destinies, beams, and field testing. Because sometimes engineers use rectangular flexural beams instead of cylinders, and sometimes they just really need to know what's happening out in the real world.
Say an engineer wants to know exactly when it's safe to strip away the wooden formwork holding up a freshly poured floor, or when they can finally open a newly built concrete bridge to traffic. A standard lab-cured cylinder won't help them with that. For this, the standard requires field-cured specimens. These samples are intentionally left out in the harsh elements. They literally have to be cured in the same manner as the concrete in the structure. If the bridge is freezing in a blizzard, the sample must freeze. If they're building a concrete pavement, the test specimens are literally left on the ground, top exposed, with damp earth banked around their sides to perfectly mimic the real slab.
Eventually, whether they were pampered in the lab or left out in the snow, it comes time to actually crush these specimens in a press to test their strength. But before we get to the smashing, we have to enter Phase 5, the paper trail, documenting the evidence. This is where the specimen's entire physical life is reduced to a meticulous, unquestionable document. Because the harsh reality is, a flawless concrete cylinder is scientifically garbage if you don't have the receipts. The lab report demands an incredible amount of data. We're talking the exact mix ID, the batch source, the precise minute it was sampled and molded. They need the absolute minimum and maximum temperatures it experienced during that perilous infancy on site. Once it's demolded, they have to record its mass to the nearest gram. And if there was even a single deviation, like say the curing box dipped to 14 degrees for just an hour, it has to be boldly declared on the report.
Which brings us to a really profound realization. We live our lives in a world of towering concrete monoliths and massive engineering marvels. Yet, the mathematical certainty that keeps those structures standing tall relies entirely on a 15mm cylinder. And even more importantly, it relies on the certified technician standing out there in the mud with a clock ticking down from 20 minutes, carefully plunging a steel rod exactly 25mm deep and tapping a mold exactly 10 times with a rubber mallet. It's a remarkable chain of trust, from human hands all the way to the written standard, holding up the very world we live in. Pretty amazing, right?